If you are here to put big models on small phones, you are in the right place. If you want otherwise, I'm sorry, we've locked the doors. You have no choice now. This is client-side deep learning optimization with PyTorch. I am Shane Caldwell. This is Tyler Kirby. Let's get started. So who are we? Why should you listen to us talk about putting models on phones? For the last couple of years, Tyler and I have been working at a local St. Louis startup, Handled. Therein, we made a bunch of machine learning solutions for the moving industry. We were recently acquired by Unigroup, who you might know as the largest interstate mover in the United States. They're behind Mayflower and United, if you see those vans. So since then, we've been in charge of technical direction and execution of the data science machine learning team at Unigroup. One of our bigger projects over the last year has been taking those sort of deep learning capabilities we built while at Handled and then moving them on to the mobile device. Unigroup has a lot more customers than Handled did. It would be very expensive to keep those models running up for server purposes. Servers cost money. And secondarily, there are a lot of use cases in moving wherein you're going to not want to rely on an internet connection to do things because, maybe the router got put away.
Yeah. So, and to give a little more background of why it matters that a moving company can put models on the phone, this is something we tried back in 2017. We had an application that truck drivers used, and they often don't have internet connection, right? We had a text classification model that was of interest. So we tried to put that on the phone. That was a disaster. It was in JavaScript. The Android got really hot. I got really concerned. So we walked away from that, came back a year later, this time working with object detection, trying to put that on the phone. TensorFlow Lite came out. We were very excited. We thought we'd give it a try. Wasn't everything we were hoping for accuracy-wise, so that was a little disappointing. And then last year, we really got involved in real-time video streaming for various applications. This is very compute-intensive. We got deep into PyTorch, figuring out how to execute multiple neural networks within milliseconds. Again, as Shane mentioned, that doesn't scale very well on the server side when you have lots of clients. So we backed away one more time, and this past year really focused on putting these deep learning models on the mobile side to improve the user experience, to improve the cost of the application. And this is sort of a narrative of what we found to be most useful in that.
Yeah, 2021 is a great time for this, as it turns out. The rest of the world is questionable, but the client-side deep learning technology, it's great. So the first question is, why PyTorch? Why not TensorFlow? When you're running a sort of a practice, a data science practice at a company, in general, I'd recommend just picking one. So you could go with TensorFlow or something like that, but we stuck with PyTorch. PyTorch has an eager execution model, so you could say that semantically it looks a lot like Python. It feels like Python, and for software developers you might be hiring who have never written deep learning code before but have definitely written Python before, it helps them be productive pretty rapidly, both in the actual development of the model, but also like when you're using it downstream, they can be pretty helpful. Tyler and I have something of a soda fetish. He doesn't like when I say that, but when we have a problem that's presented to us, we like to look for, what the state-of-the-art solutions are. So we'll go onto Archive and Google, like, hey, how do you do this, but make it harder? And we can't re-implement all these papers because there's not enough time for that. So in general, we'll only go with solutions that have code published. And we found anecdotally, if there is code published with the paper, that code is probably written in PyTorch. And though that anecdotal evidence that feels good is backed up by data from papers with code that makes my brain believe it's true. So we stick with PyTorch for that reason. So this was us about a year ago. Server side, it was expensive. It was kind of slow for the applications we were working on where FPS really counts. Let's put it on the phone. Tyler is endlessly confident. He says, how hard could it be? Could take 1 week, could take 2 weeks. We told that guy it would take that long. We were wrong. This is more what it looked like. So we spent a long time expecting that it was going to be easy, and then more time looking at stack traces. I initially had a sea turtle here, and the people I had sort of preview this talk told me that sea turtles are actually pretty fast, so I had to replace it with the tortoise. Anyway, the point of this talk is to get you from sad baby to happy baby in terms of putting models on phones. So if you or someone you love has written PyTorch, you'll know that this is basically what it looks like. This is an eager module, the sort of most vanilla PyTorch. It's really easy to work with. You just inherit from this nn.module class. You will have a forward function that takes some input and applies all these nice tensor operations to it. You'll return it. That's convenient because Python is not going to do any of that math, right? In general, if math is being done, we're going to pass it off to someone else, usually C++. But what PyTorch makes really convenient is passing up those kernel level code executions back up to Python's process. So after each of these things is done, you can sort of step through it in your standard debuggers like PDB, and that makes unit testing and debugging super easy. So another reason we love eager execution. But if you want these things to run really fast, then you sort of have to look under the hood. So PyTorch is great for people who are getting started to focus on data science-y things. So like, how am I loading my data set? How am I going to handle my learning rate scheduling? What's my hyperparameter search look like? All that stuff that the kind of the level of abstraction they prefer to think on. So for prototyping, that's great, but to go to production, you have to think a little bit more about the context in which this code is getting executed and sort of the theoretical underpinnings of like the actual math getting done. And that sort of this talk is about getting you from that research and production context that data scientists usually handle to the production deployment one that's more ML engineering-y.
Okay. So as a data scientist, you have choice unlimited in many different things, how you optimize, how you choose your algorithms, how you go about your work in general. And it's useful to have sort of guiding abstractions to more quickly lead you to the right method. So we've used this axes of optimization abstraction to sort of think about what direction we need to take our optimization project next, right? So beginning with inference speed, this is typically the most important. If you're putting it on a phone, you're going from a high compute environment to a low compute environment. The model is usually going to be slower out of the gate. You're expecting that, and that's what you're trying to solve here. Accuracy, obviously, if you optimize a model and it does worse and you don't solve your problem, you have new problems, and that's not great. So we need to be keeping track of, are we still able to solve the task with the sufficient threshold of accuracy that's required while ruthlessly optimizing for performance? And then finally, binary size. This may seem a little out of the blue here, but it's a really good metric to be tracking as you're optimizing your model, and we'll talk about these interactions for why that's true. So let's talk about inference time a little more. This is your primary metric to understand the efficacy of your optimization methods. It has an adversarial relationship at times with accuracy. As you're able to improve your inference time, it might be at the cost of accuracy. So be mindful of that. There are some things out of the box that are going to make your model faster and not worse, and we'll talk about those. But those are pretty few. You are going to have to make some trade-offs ultimately. And how you measure accuracy is also super important, right? So you need to be aware of the available threads on the computer that you're benchmarking your models. You need to be aware of background processes, all these things that could affect the validity of your measures of computation. And because of that, we typically, throughout the first few rounds, burn in rounds in general to sort of ignore those effects. Right? And then a little more about accuracy. This is pretty straightforward, but we do want to call out that it's important to have multiple metrics for accuracy. So one thing we found when working with an object detector, for example, if you only use some aggregate method like the mean average precision, and then you do various optimization methods that may affect the performance of your regression accuracy unevenly compared to your classification accuracy, you're not going to catch that so readily, right? So you need as many accuracy and evaluation metrics as possible to understand how optimization methods can unevenly affect the performance of your model. And then finally, binary size, right? Big models are typically more accurate and slower. Small models are faster but less accurate. This doesn't quite work out that neatly, but in general, that's a good heuristic for thinking about it. It's also useful to think about how many parameters you need to solve your problem. Typically, when we're talking about how big a problem is, we're talking about, or how big a model is, we're talking about how many weights do you need to represent that model. If you're able to solve your problem with fewer weights, do that, right? And, a lot of modern deep learning encourages extreme over-parameterization, but you don't really have that luxury on the client side. So you need to be using architectures that make the most effective use of the parameters available to you.
So, eager PyTorch, that's great, but it won't work for production. So eager modules have a couple of problems, one being they're bound to a Python runtime environment. So Python, while we love it, it's not available everywhere, and it's not exactly desirable everywhere it is available. So we can think of mobile devices or cars or toasters, I guess. The Python runtime environment is crucially bounded by that global interpreter lock, which makes a lot of things easier, but means you will not have true multi-threaded inference. So to get the same throughput you would get without the GIL, you're going to have to scale up more sort of server-wise, and that, again, gets expensive. So these eager modules are bound in portability, where does Python run, and then in performance because of the global interpreter lock. So we want to escape these sort of restrictions in order to keep using our PyTorch models, particularly in contexts like mobile devices. We are not the only ones with those problems. PyTorch considered it. I'm sure Facebook was very interested. So your PyTorch model, if it subclasses from nn.module, is an eager module, as we've discussed. And PyTorch allows you to take that eager module and create an intermediate representation of it, and that's called torch script. That runs in a separate interpreter that runs a subset of Python operations, but crucially with no global interpreter lock. So you will be free. This gives us access to what is called graph execution mode. And the interpreter is just in time, meaning that optimizations are going to be performed over the runtime of the program. And we'll get into what that means a little bit more. So the just-in-time compiler allows you to serialize your eager execution modules in PyTorch into TorchScript, but that process is not automated. So you as the practitioner have to make a couple of decisions in terms of how you're going to do that. There are multiple techniques, and we'll cover them quickly here. There is tracing, scripting, and a combination of the two. So first is tracing. You're going to declare an input to your neural net. You will push it on through. There's this data structure called gradient tape that'll look at all of the tensor operations that you're applying. So you'll think of like the eager module I showed you earlier. That would be them. So it'll just take a look at that gradient tape at the end and say, okay, that's the torch script, that's what it is. So if there's no control flow, there's no if statements, then this is sort of the right call. And if you're not using a lot of Python data structures. You can imagine because we are doing, again, one input to tracing, if there's any if-then that would cause it to go down two separate routes, well, you're only going to trace the one. So then you're going to start, your intermediate representation won't represent the eager module. Scripting is different. It handles that control flow and it handles a whole bunch of Python operators. And I will say over the course of my time using TorchScript, it continues to sort of include more, which is great. That means it's like mostly Python though, so it's not that much faster than just Python, except for you get rid of that global interpreter lock. So it is still worth the price of admission. And it doesn't require a sample argument because it's going to use recursive static analysis in order to get this done. So if your model is not just a function, this is true of like many sort of modern techniques that are going to use more Python data structures. This is where you should go. And there is nothing legally stopping you from combining the two. So if you really want to get more performance out of your model, these neural networks, people talk about them like Legos, and that's like not entirely incorrect. They're pretty composable functions. So if you break off the parts that require scripting, you script those, take the rest that don't need it, trace those. You can kind of stick them back together. I will say the process in reality is a little more complicated than that, so if you can avoid it, just stick with scripting. But if you need that performance, you can get it. So intermediate representations, they come from compiler theory. So obviously we want them to fully represent the sort of program that was written in Python. If our inputs and outputs are not the same, then we're not interested, right? The format is generally going to be simple. So if you have a big compound statement, it's going to break it up into simple ones that are easy to automatically optimize. So this is sort of just a generic IR example. In PyTorch, you can look directly at your intermediate representations. This is useful because PyTorch is going to have a bunch of different optimizations that it can do, but if you want to know what is actually happening, you're going to want to interrogate your serialized script at multiple points so you can see like, hey, this is what actually changed. If you call .code on a serialized Python or PyTorch model, you'll get this sort of Python-looking syntax, which is nice, but a little detail light. On the other hand, if you want to get really into it, you can call .graph, and that's going to give you a lower level representation, and this is a level on which optimization is actually going to be performed. So if you want to see what your optimizations are actually doing, then call .graph, do some optimizations, call it again, do that diff with your eyes, and then you understand, okay, this is what's actually changed on the torch script level. You can also write torch script raw if you want. There's nothing stopping you. I don't recommend it. Keep in mind that eventually an interpreter is going to be optimizing this code as it runs, and it's way better at optimizing the stuff that PyTorch generates itself than the stuff you would write by hand. So now you have this serialized module. You're away from the GIL, but you're still in Python. That makes you mad. So we're going to export a .pt file, and that's just going to be a zip that essentially gives you everything you need to get out of the Python runtime. So everything, the code, the weights, the constants, debugging information, that's going to be all available in this, what is literally a zip file. This is what it looks like if you unzip it. There's nothing you can do with that, but it's kind of interesting. So now you have everything you need to run the model without Python. So now you want to run your torch script. It's going to run in C++. So the dirty secret, or the not so dirty secret, was that Python was already having all of its tensor operations and its autograd engine. That was all happening in libtorch anyway, which is C++. So now that you're away from Python, you have this PT file. Anything that can run C++, which last time I checked is basically everything, can now run this sort of deep learning model. So all that stuff like, Torch.js, GoTorch, HasTorch, RubeTorch that I'm sure exists, like all that stuff is actually just languages that have written these bindings to talk to libtorch. A couple of speed tips, do not forget these. If you don't call model.eval, so that is putting your model in evaluation mode, so you're saying, hey, we're not training. If you don't do that, they're going to start tracking like gradients and doing all those things that you need when you're training a deep neural network. If you do all these optimizations, but you leave your model in training mode at runtime, you're just leaving speed all over the floor. And I did this for like months because I didn't even think. I was like, why would you train in C++, You also want to warm up your model, right? So these optimizations are performed just in time. So those first couple of runs through the model, you're sort of teaching the interpreter like, hey, this is what my input's going to look like. I don't need, my gradient or what have you, and it's going to learn, okay, I can throw some of this stuff away. I can optimize that torch script we saw earlier, so that compute graph is going to look real nice. Also, cache that. Keep that in cache once you've got it all nice and warmed up and loaded, because you just did a whole bunch of work, and you don't want that to get garbage collected, because then you got to do it again, and you're going to get slow for no reason. And if you're me, that'll take you a month to figure out. Then, if you want to get really nitty-gritty, right, you're really caring about size, your footprint. If you're shipping an app to the App Store, it's going to ship with like libtorch included, and that can get sort of hefty. But Torch has thought of that as well, because they're very nice to us. You can export the literal operator names of what is going to need to get executed for your model specifically into a YAML file. Then you can use a static linker to prune literally everything besides the operators you need to execute your specific model. So that means when you ship your app, it's going to take up less space. It's going to give you a smaller footprint and slightly faster execution for your trouble. This is sort of a weird inside baseball thing. Hopefully you guys remember this later. Keep in mind that while you're running this stuff in C++, the actual interpreter is not in C++, right? So when you're loading your model and running inputs through it, you're not going to get compiler time warnings. All the compiler is going to look for is that you're passing a vector of interpreter values. So basically, regardless of what the actual model is expecting at runtime, it needs to be a vector of these interpreter values. Here you can see that in this RCNN example, that is expecting a tensor list. This is a little sort of novel in terms of inputs models expect. I have to sort of jump through all these hoops to make sure that I create a tensor, and then I put it in a vector, and then I put that in a tensor list, and then I put all of that in a vector of I values, which is actually expected. At that point, Xcode stopped yelling at me and let me run this. So you don't need to know the specifics, just know you're going to need to look at the actual runtime errors to determine what you should be doing to your input to let it run through the model. And there's a Lite Interpreter. So I hate to break this to you, but if you're watching this talk in the future, some of this stuff is going to have changed. So PyTorch has recently released in beta a Lite Interpreter for mobile. So we didn't use it in our experiments because we don't put things in beta in production. Come on, when we can help it. But going forward, it's likely to be the preferred method. So you're probably going to get a lot of like, you know, the binaries are going to get smaller and the interpreter is going to get faster, and that's all going to be free. So if you can wait, maybe just wait. You'll be able to recognize those artifacts because they'll be called PTLs because they're light instead of PTs. Our experiments showed that they were essentially like equivalent to the JIT, slightly slower in some cases, but the binaries were a lot smaller. So if you're watching this on YouTube, you use the Lite Interpreter.
Okay, so let's talk about quantization. So now we know that we can take our PyTorch model and serialize it for a runtime on the client side. But how do we go about actually making the model faster, as accurate as possible, et cetera? Quantization is the primary method in machine learning nowadays for doing this, and the idea really comes from digital signal processing, where we have some continuous signal and we want to approximate it with some discrete lower memory representation, and that's exactly what we're going to do in this context of machine learning. So PyTorch very nicely has supported the most common methods of quantization since about March of 2020. They have two primary methods of quantizing models. They're going to work on both the eager mode representations that we discussed earlier, as well as the traced methods working on the intermediate representations in FX graph mode. FX graph mode is pretty new. We didn't try it a whole lot because it only came out in the last month or so. So we primarily worked with the eager mode. So in the future, when you're trying out TensorFlow Lite Interpreter, or I'm sorry, PyTorch Lite Interpreter, you might as well try out this FX graph mode as well. So let's get into what these methods and algorithms actually are. Dynamic quantization, static quantization, and quantized aware training are the three big ones we're going to discuss today. They are sort of mutually exclusive in that you wouldn't do both dynamic and static quantization. They have different required effort from the developer. We're going to see dynamic quantization is literally one line of code, whereas quantized aware training can take about a week to retrofit your code depending on what architecture you're using. And the choice of architecture is going to be very important here as well. Because of how these quantizations are performed, language models may prefer some methods and vision models may prefer other methods. All right, so let's start with dynamic quantization. There's really two things happening here that are important. The first is that our weights are represented as 32-bit floating points, and that takes a lot of memory. So the first thing we're going to do is reduce the precision of these weights to 8-bit integers. The way that we do this is pretty simplistic. It's pretty much min-max scaling. We can do this because our weights are finite static sets, right? They're not going to change at time of inference. We've already done the training. We know the minimum and maximum of our weights. We can do this scaling. The other thing that we need to account for, though, are activation functions. When you take the output of quantized weights and inputs to a nonlinear activation function, your output may not be sufficiently quantized, right? So we need to learn a scale factor for the output of these activation functions. This is where dynamic comes into play, because in this case, that scale factor is going to be determined at runtime as it sees new data. Because at time of inference, that set is not finite or static. You can have data across the whole spectrum. In theory, you need to be updating that scale factor based on the data you see. So static quantization is really most useful when the burden of compute is coming from loading lots of weights and batches off of disk, loading that into RAM, right? So this is typically going to be seen in language models, transformers, LSTMs, RNNs. They benefit greatly from this method. They have a lot of weights. Typically you're working with batches in language context, even at time of inference. And luckily, it's the easiest method to apply. Literally, these 4 lines of code up here will take your language model, your LSTM, whatever you want. In this case, we looked at a mobile net and sufficiently quantized it. All right, so just to illustrate what we mean by min-max scaling the weights, it's kind of a quick example. We have some random Gaussian distributed matrix here. Pretend these are your weights. They are 32-bit floating point representation. That's taking up a ton of memory. We know the min and we know the max, and we know those aren't going to change. So, very easily in a line of NumPy, we're able to reduce the precision of this to 8-bit integers. All right, so next we have static quantization. We're still going to quantize the weights like we did in dynamic quantization, but now we're going to take a closer look at how we quantize the outputs of these activation functions. So rather than waiting to time of inference to have some running determination of the scale factor based on the data that we see, we take the data set that we already have available to us and use that to calibrate the scale factors of these activation functions. This can also be done on a per channel basis, which is really helpful in a vision context, right? Because your vision models are going to have many different channels, your inputs will have many different channels, and if you learn a scale factor per channel, you're going to get a better representation of those weights in the 8-bit integers, right? So this is going to benefit vision models more than language models we found. It does require a little more work. This isn't a one-liner. That's why we didn't show it. It's a lot of lines of code depending on what you're doing. And that's because you need to stub out functions in your custom PyTorch code if they don't have some quantized corollary. So if you're working with a very custom architecture that's very large, this could take a long amount of time. If you're designing a network from the beginning, knowing you're going to quantize it, then you can have that selection of quantized operators to make sure that you're not going to have to retrofit this later. What we would actually recommend is if you know you're going to need quantized static quantization here, and you are doing a vision model, pick one of PyTorch's pre-quantized architectures like MobileNet v2 or MobileNet v3. These are going to be great options to start with to fine-tune. They outperform some of the more exotic models that we've tried in the past, and it's going to save you a lot of pain in the quantization process. So quantized aware training takes this idea of using the data set to learn these scale factors for our activation functions one step further and asks, can we do a couple forward and backward passes in our network in a fake quantized environment? We force rounded integers or something to coerce the model into behaving better under quantized conditions, right? Can we fake quantize, put these constraints on the model, and see if it can perform better in low compute environments? It's kind of similar to regularization, right? We're putting constraints on the model to make it learn better. In this case, can it learn to work with this 8-bit integers? This method is really only necessary for when you tried static quantization at the per channel level, you didn't get the results you're hoping for, accuracy dropped dramatically. In the PyTorch tutorials, you'll see that they use a MobileNet v2 to kind of illustrate these ideas. A MobileNet v2 on ImageNet classification typically scores 72%. After static quantization, that dropped to 57%, pretty bad. After doing the per channel quantization, that jumped up to 67%, better. And then quantized aware training brought that to 71% or so. So almost back where you started. Well worth it if you're not getting the accuracy you're looking for. All right, so we did some experiments with a couple different architectures here, really to just show the benefits on real models. So we took an LSTM with a pretty large embedding layer, a LSTM cell with a ton of hidden layers, and then a final linear layer for some classification text. The base model was 169 megabytes, and its inference speed on a batch size of 32 was about 5 seconds. So after dynamic quantization, we reduced that to 134 megabytes, and the inference speed dropped to 1.6 seconds. And then looking in the vision context, we took a MobileNet, already a great architecture for a compute-constrained environment like a phone. Its baseline is 22 megabytes in size, 0.13 seconds of inference and classification, and then it has a ImageNet accuracy of 74%. And then we performed static and quantized aware training on this, got this down to 5.6 megabytes, 0.03 seconds of inference, and finally 73% accuracy. So losing 1 degree of accuracy, but dramatically increasing performance of the model. Here's a brief flow chart if you have to make a decision and you really don't want to kind of guide you to the right quantization method. If you are working with a neural network that you want to quantize, ask yourself, where's the burden of compute coming from? If it's coming from loading weights off a disk and passing big batches, like a language model, do dynamic quantization, you'll probably be fine. That's really all you need to try. In a vision context, you'll probably want to start with static quantization. If the accuracy was reduced too much to solve your problem, now I'd suggest trying quantize-aware training. All right, and then very quickly we have additional optimizations. These are kind of freebies in here. So the first of which is module fusion. The idea here is pretty basic. There are some operations you do all the time in a neural network, like batch norm and then a ReLU activation function. You can fuse these into a single instruction so that when it's executed in Torch script, it's 1 instruction instead of 2. The optimize for mobile method in PyTorch will do this for you. If you have large convolutional block networks like a ResNet or something, this is going to give you a little more performance. Channel last format is a really cool idea. It's really useful in this context where you're working with images in batches at time of inference. But typically, an image in PyTorch is going to be a tensor with 4 axes batch height width channel, right? Imagine you had an image with a large black patch. The pixel intensities in that area for each channel is going to be the same, right? So if you have the channel in this second position, that's not the most efficient representation to hold this tensor in memory. If you move the channel to the last position, however, areas of the image where the pixel intensities are the same can be stored more effectively. So now PyTorch's mobile APIs in iOS and Android support this channel last format when you're working with image tensors. Okay, and a quick addendum. Some things that we've mentioned in the abstract but didn't quite cover yet because they're not problems anymore, like operators. So when we first worked on this talk in May or so, we were working with the network. It used non-maximal suppression like most object detectors do. This was not supported in PyTorch's mobile APIs. It was incredibly painful to load up that operator intentionally in the mobile application.
He wrote his own implementation in Java.
Yeah.
It was a disaster.
It was really bad, very painful. Not a problem anymore though. So Torch Vision on mobile supports these operators natively. In general, we'd recommend that don't get too novel when you're going to the client side, right? Architectures matter, mobile nets are really good. Don't be using the activation function of the month and then writing a custom operator for it and trying to load it into PyTorch. Stick with what they support. They support a lot more now, and they'll generally make your transition to the client side less painful.
In conclusion, so we threw a lot at you. You're all very brave. But some takeaways, so when you're home thinking about this stuff, make sure you're using Torch script for your modules, right? So if you're not, if you're running eager execution in prod, go home, serialize that, make that Torch script. There you go. Your life just got a lot easier. I just saved you a bunch of money on server costs. You can Venmo me. When in doubt, use torch.jit.script. So if you're using a model that you're not sure sort of how to serialize it, script is basically going to do the job, particularly if you're taking a model off a model hub somewhere. Script is the way you want to go. As we've said, architecture is going to be greater than optimizations in this case. So there are some models that just aren't going on the phone. GPT, it's not going there. In those cases, you're better off looking around for sort of model architectures that were designed for low compute environments, like MobileNet. It's got mobile in the name. That's going to do a lot more for you than these optimizations. Assuming you've picked a good architecture for your use case and you're still needing that performance, quantization is like, if we're talking 80-20 rule, quantization is that 80. Start there. If you do that right, you're going to get a lot faster for relatively low work. And I just want to say, like, we're saying all this stuff like it's like, oh, super novel, but PyTorch's documentation is fantastic. This stuff is all there. Make sure you understand what it's saying and you implement all the tips they recommend. That's going to save you a lot of time and heartbreak and get you to happy baby faster. All that stuff's going to be better than these sort of implemented custom operators, because the stuff someone else wrote is going to be faster than the stuff you wrote. So that's it. Thank you. If you have questions, you can email me. I'm on Twitter too much. You can find me there. You can also tweet at him, but he's on there very rarely. You can email him, though, and he will see it. Thank you all for coming out. You've been a wonderful audience. Have a good one.